All right, let's continue our lessons with circles. And so we're going to talk about some angles and arcs. You probably don't even think about angles when you think of circles, but we do. We have quite a few angles. So let's put a circle right here. And let's talk about, first of all, what an arc is, and we'll talk about the angles. So if I did this, actually, let's talk about the angle first. All right, measuring angles, then arcs. So let's put line segment right there, line segment right there. Those are both radii of a circle because it goes from the center to a point on the circle. What happens is, if you put two of those, it creates an angle, this angle right here. And notice the vertex of the angle is the center of the circle. So that's basically called a central angle. So that angle right here with the vertex as the center of the circle, that's called a central angle. And there's something very important about the central angle. I don't think they say it right now, but I might as well just tell you right now. The central angle is actually equal. Well, I haven't even talked about an arc yet. Getting ahead of myself, but I'll say it anyway. The central angle is equal to the measure of the arc that it cuts off. We'll talk about what an arc is in a little bit, but just right now, understand that this is a central angle. Of course, I could make more central angles. Let's do this. Click that right there and watch. Okay, that right there, that's another central angle. It's a bigger angle, but it's still considered a central angle. See if that still works. Yep. I can keep going all the way around. That's another angle. This angle right here now would be the central angle. Of course, not that one. All right, as long as the angle has the vertex at the center of the circle, then that would be considered a central angle. And again, I kind of alluded to it. I shouldn't have this early on, but it will equal its arc, which we'll talk about here in a second. Let's just talk about the central angles here just for a minute. Let's draw something that kind of looks like if they call it the key concept in the book. It's kind of like an example. So let's just draw that first before we move on. Okay, here's something that we should probably be able to figure out on our own, I guess. But we'll talk about it right here. I've actually have, well, I guess you could look at several different angles, but I'm looking at three of them. I'm looking at this big angle right here. We'll call that angle 1. It's not quite 180. Okay, I just kind of made it look like they did in the book. It's not exactly 180. It doesn't go all the way straight through. It kind of bends off a little bit as it's coming through here. So that's angle 1. We'll call that angle 2, and we'll call that angle 3. So if you take a look, watch this. If I start at 1 and go to here, and then I go a little bit more, angle 2, and then I add that angle 3 to it, look what it just did. It created a whole entire circle. And how many degrees in a whole entire circle? 360 degrees. So if I was to add up all the central angles of a circle, I could have had 4 or 5 or 6, or how many I wanted, central angles coming out of this. All those angles would add up to be 360 degrees. So the sum of all the central angles will be 360 degrees. They call that a key concept. It's not really a theorem or anything like that, but it's good to know because we're going to use that. Let's just do a quick example on how we're going to use this stuff. Okay, here's a quick little example on this. They're going to ask you to solve for x. So they'll say solve or find. Sometimes I think they'll probably say find, or find the value of x. I'll just say solve. So if you're taking a look at this, you want to find what x is equal to. So how are we going to do that? Well, you got to remember that the sum of the central angles is 360 degrees because it forms a whole entire circle. So right here, I've got 90 and 130. So 130 plus 90 is what? 220. All right. Of course, this is not 220, but how am I going to find what's left over? Okay, I already know this. I know this is 220. So what's going to be left over? Yeah, I take the difference of 360 and 220. So 360 minus 220, and that is 140 degrees. So x is 140 degrees. Really not that difficult. Again, the only concept here is what we're trying to learn in this little section is that all of the central angles add up to 360. It's the same kind of stuff we've been doing all year, except now we're talking about the central angles of a circle, which we've never talked about before. All right, let's move on to something else. Okay, here I have a circle with a central angle, and I've got some letters on here. Let's just talk about this next thing. This is what I was talking about before when we were talking about arcs. So I want to see what in the world is an arc. Okay, where was I? I paused it for a while and had to take care of a couple things. Now I'm back. So let's see. We were talking about arcs, so let's talk about how to label the arcs, how to name the arcs. Well, first of all, what really is an arc? Let me make this a little thicker so I can kind of draw around here. Got to have a kind of steady hand. But what are we talking about the arc? We're actually talking about a portion of the circle. All right, so this, I'm trying to trace around this as best I can. So that right there, and let's make it a different color. Let's make it blue. Did I make it blue? No. Gotta click on it. There we go. And now we'll make it blue. There we go. So that part right there, I'm not very good at coloring on the line, but anyway, that part right there is considered an arc. Now this other part right here would be considered an arc as well. So it's a portion of the circle is what an arc actually is. So we need to learn how to name these arcs and actually give it a symbol. So let's do that for this arc right here, this blue one. So if I wanted to name this blue arc, I would name it arc PR. It doesn't matter what order you go in, as long as you have the endpoints. See how that's an endpoint of an arc and that's the endpoint of an arc? As long as you have the 2 points on there, that's good enough. Now, what's the symbol for arc? We don't write the word arc in front of it. We actually kind of make an arc looking thing over top of it. So that's the symbol for arc PR. Okay, again, I could have called it arc RP or PR. It doesn't make any difference. What about this one down here? Oh, by the way, look at this. This right here is less than 180 degrees. When I say that, I mean if this was going to go straight here, this would be less than half a circle. We'll talk about half a circle in a second. So if I took this and I extended it all the way to here, that would be half the circle. If it's less than half of a circle, I call it a minor arc. Or if it's less than 180 degrees, I call it a minor arc. What if it's more than 180 degrees? Well, less than would be a minor arc, so what would be more than? I think you got that. It would be a major arc. So a major arc is going to be greater than 180 degrees. And I can actually name the major arc right here. Now, let's try a different color and see if I can do it again. Now, I've got to be careful, but anyway, I'll just try to trace along this line. Oops. Kind of let up on it. That's close enough. So that pink arc, pink or purple or whatever color it looks like, that right there would be a major arc. And it's a major arc because it's more than 180 degrees. See, again, 180 degrees would go here, and so it went from here, and it went more than 180 degrees, more than halfway around the circle, and that would be a major arc. Now, we can't just call it PR, because look, it does have an endpoint at P, and it has an endpoint at R. But if I just called it arc PR, you wouldn't know you wouldn't know which one I'm talking about. You wouldn't know if I'm talking about this minor arc or this major arc. So what we do is to show the difference between a minor and a major, we stick an extra point in there. Right here, if I just said arc PR, and I didn't even say major or minor, if I just said arc PR, you would know I'm talking about from P to R in that direction. I'm not going from P to R in this direction. So if I said arc PR, it would just be this one. But if I said arc, what do you think? PSR, then that would be a major arc. So if I said PSR, then that would be a major. All right, so if I use 3 letters, it's going to be a major arc. If I only use 2 letters, it's going to be a minor arc. Well, what if this thing went exactly, oops, I don't want to do that. I want to grab the end of it. There we go. What if it went like this? Okay, so watch this. Let's get rid of some of these things right here, and let's get rid of this pink arc. Let's see if I can get rid of it. Nope, don't want to get rid of that. I want to get rid of, let's see, there we go. That's what I want to do. Oh, I got a little extra on here. Okay, so what if I wanted to talk about just halfway around the circle? Let's use that pink color again. And so let's try to trace halfway around the circle. It actually wouldn't matter which direction you went. Well, I guess it kind of would. Watch. Let's go in this direction again, and I'm just going to go halfway around the circle from here to here. We'll call this T, all right? a little thick, but you get the idea. So from T to R. Now, which direction are you going? That's very important. Are you going this direction? Okay, or are you going down this way? All right, and that matters because they're two different arcs. This arc is kind of below, this arc is kind of above. They would be two different arcs. But if you look at it, we can't just say TR because you wouldn't know which one I'm talking about. So just like with the major arc, we want to use 3 letters to go halfway around the circle. So I would call this arc TSR. Now I could have called it RST. That doesn't make any difference. As long as S is in the middle, okay, the T and the R are the endpoints. You see that? The S is in the middle, and that's what we can call it. So we could call it arc TSR. So that pink arc right there would be TSR. Now we don't call it a major arc. We call it a semicircle or semicircle, however you want to say it. I probably would say semicircle. So it's a semicircle if it's halfway around. So again, a minor arc is less than 180. You might want to write that down. I just kind of ran out of room here. This is less than 180. This is more than 180 degrees. And this is exactly equal to 180 degrees. And we're going to refer to these quite a bit. So I think it's important that you understand which arcs we're talking about. So if I said arc TSR, you know you're talking about this one. What if somebody came along and say, hey, yeah, but look at arc, let's say RPT. Well, you would be talking about this arc right here. Now, they have the same measure. They both go halfway around the circle, but they are different arcs. All right, I hope that makes a little sense. I kind of talked about this earlier, but now I think we can officially say this, that if we have a central angle, this is a central angle because this is the center of the circle. It's the angle that's created here. It's at the vertex. The center of the circle is at the vertex of that angle. This angle right here is called the central angle. We have it's not really a theorem. I thought it was a theorem or something, but they just kind of mentioned it in this little box called the key concept in the book, if you want to look at that. That's on page 693. What it says is this. It's very simple. It says that the measure of the central angle is equal to, or congruent to, the measure of the arc that angle cuts off. All right, so watch. This goes to here. This angle goes from the center to A, and from the center, we'll call it C. From C to B, there's my angle right here, angle ACB, or just angle C. That angle is equal to the arc that it cuts off. So where does it cut it off? Right here and right here. And so if I wanted to, I could kind of trace around here. So that green arc, let's make that look a little thicker so we can see it a little bit better. There we go. So that green arc right there has the same measurement as this angle does. And so if the angle is measured in degrees, let's just make something up. Let's just say that's about 150 degrees. If this is 150, it's probably a little less than 150. But anyway, if that's 150 degrees, then the arc is also going to be 150 degrees. So if they just stick a 150 right here, and it's in between the A and the B, that means it goes from A to B. So that's 150 degrees. So the central arc is equal, the central angle is equal to the arc that it cuts off. We say it cuts it off. It hits it right here and it hits it right here. All right, so the central angle is equal to its arc. That's very, very important. Now, what if we wanted to find the other arc? And we need another letter in here. We'll put a D right there. It's supposed to be a D. There we go. All right, so look at this crazy angle right there. All right, I'll just put a couple arrows just to indicate it. So what about that angle? What in the world's that going to be? Now remember, all the central angles add up to be 360. So I just take 360 minus 150, and that's what? 210? So this arc right here is 210 degrees. So if I asked you, what is arc ADB? ADB is the arc that is cut off by this big 210 degree angle. All right, so I'll try to draw it. So this all the way around to there. All right, so that yellow arc right there is the same as this yellow angle. So that would be 210 degrees as well. So we could say, they'll ask you, they put a little M in front of it. I don't usually do that, but watch this. What if they say, what is the measure of arc AB? You would just say 150 degrees. Or you could say, what is the measure of arc? Now you can't just say AB again for this yellow one. Remember, it's a major arc. It's more than 180, so you got to put that D in there. So it's going to be So what is the measure of arc ADB? That would be 210 degrees. Those arcs all add up to a whole circle, which is 360. Those do add up to 360. Hope that makes a little sense on how to name these things. Okay, this is arc AB, this is arc ADB, and those are the measurements of those particular arcs. Let's do a quick little example that kind of helps understand this a little bit better. All right, let's look at this situation. They got 3 questions right here. They say, what is arc GH, what is GLH, and arc GLJ? So let's start with the first one. First one's pretty easy. It's just arc GH. So I'm going from G all the way to H. So what is that arc equal to? Well, if you look, they give you the central angle. They give you the angle that cuts off that arc right there. So if this is 122, it cuts off arc GH, and so the arc is equal to the central angle. So that's pretty easy, no math whatsoever. It's just 122 degrees. All right, let's look at GLH. There's G, there's L, there's H. So we got to take a look at this big old arc. Let's do that in a different color here. So we got to look at this arc from G through L. Oops, oh my goodness. A little shaky on that one. Must be nervous. Not really. G, L, H all the way. Ooh, that's pretty good. Oh yeah, look at that. That's off a little bit, but you got the idea. So we got to take a look at that big old arc right there. Well, that arc is everything except this arc. Remember, this was 122 degrees. This yellow arc right here is everything else. So how do you find it if it's everything else? It's everything else from what? From 360. There's 360 altogether. We just take away 122. And when you take 122 away from 360, you get 238. And so that's what this yellow arc right here is. It's 238 degrees. Okay, arcs are also measured in degrees. So let's move to the next one. The next one, let's change colors here. Let's go, oh no, let's go red. All right, GLJ. GLJ, that goes from here, and then it goes through L, and it stops at J. If you look at this, from G to J is a semicircle. It's a that's 180 degrees. And how do you know that? Because it's a line that goes through the center and it just keeps on going and it hits J. So this is a semicircle. And how many degrees is a semicircle? No work needed. It's just 180 degrees. So that was pretty simple. This is the only one where you had to do some math with. All right, hopefully that's making a little bit of sense to you. Let's go over a couple more things. All right, this is a theorem. It's actually the first theorem of this chapter. And to me, it's kind of self-explanatory, really. If you look at it, what it says is this. If I have two equal, let's see, the central angles. If I have two central angles that are equal to each other, watch this. If this angle 1 is equal to angle 2, and remember, FG, so let's write it like this. So if angle 1 equals angle 2, then what do you think we can say about the arcs? Well, look at the arc that angle 1 cuts off. That's FG, isn't it? Arc FG, put the arc symbol over top of it. So remember, the arc is equal to the angle. So whatever this arc is the same thing as angle 1. Well, angle 1 and angle 2 are equal to each other, so guess what? The arc opposite angle 2 has got to be equal to the arc opposite angle 1, because 1 and 2 are equal to each other. So arc FG must equal arc, we'll call it JH. All right? Again, that's kind of common sense if you understand what a central angle and the relationship between the arc and the central angle. So if angle 1 and 2 are equal to each other, we know that the arcs are going to be equal. Well, we could go the other way as well. We could say, well, what if you didn't know? Let's get rid of some of this stuff. What if you didn't know that the angles were equal to each other? What if you didn't know those two central angles were the same? But what if you knew, and we can do this with arcs too, we can put a little tick mark. What if you know that arc FG was equal to arc JH? So let's write that down. So if arc FG was equal to arc JH, again, I think this is pretty easy for you to see. If those two arcs are equal, what does that mean about the angles, the central angles? Sure, they're going to be equal to each other as well. So it seems like it's saying the same thing, but you're starting off with different information that you're given and that you know. So if arc FG is equal to arc JH, then angle 1 is going to equal, not comma, equal angle 2. And of course, they're going to put numbers in here, right? You're going to be able to figure out what the arcs are equal to and all that kind of stuff. They could make this like 3x plus 2, 5x minus 1, or something like that. You might have to solve for x, plug it back in. You've done that whole thing. That's routine for you now. You've done that thing all year long. It's just getting to know the relationships between the angles and the arcs and all that kind of thing in the circle. All right, let's do something else. Okay, the next thing I don't think is that hard either, but we got to talk about one definition right here. We're going to talk about adjacent arcs. We've used the word adjacent quite a bit before, and we're going to talk about adjacent arcs. It means things are next to each other. So let's take a look. You could probably guess already which one the adjacent arcs are, and I think you would be right. So HJ is an arc. Which one is it adjacent to? Well, it's adjacent or next to this one right here, which is, they're not necessarily equal. I'm not putting an equal sign here. I'm just saying that they're adjacent, and those are the two. I've just listed them with a comma in between. So this arc right here and this arc right here are adjacent to each other. How do you know they're adjacent? Well, what they do is they share a common point at point J, and that means that they are adjacent arcs. All right, let's talk about another theorem that has to do with this adjacent arcs. All I did right there was just kind of give you a definition. Let's talk about the next theorem that they have in Chapter 10. All right, this is a theorem, but again, I think it's kind of common sense if you take a look at it. They call this the Arc Addition Postulate. It says this. If you have two arcs, it says the measure of an arc formed by two adjacent arcs. Okay, these are two adjacent arcs. So ZY and XY, those two arcs right there, they're adjacent to each other. It says if you take the one arc and add it to the other one, it's going to make this one big arc. All right? Doesn't exactly say that in the book, okay? It's a little more eloquent than I just said it, but it's basically saying this, that if you had arc, let's say XY, right? And if you added it, so that's this arc right there. I'll just kind of make it a little thicker. All right, so if you take that arc right there and you add it to the adjacent arc, which is YZ, it's going to equal the whole entire arc from X to Z. So X to Z. All right, see how you have the Y in between both of these? XY, then YZ, then XZ. Again, it's kind of self-explanatory, I think, but that's a theorem. Okay, that's a theorem, or a postulate, I'm sorry. It's not a theorem, it's a postulate. It's not something that can be proven. It's something you just look at and you say, yeah, that's right. And that's kind of what we've done right there. Let's do a quick example, then we'll move on to our last topic. Here's an example that talks about what we were just doing right there. Well, it's kind of, yeah, I guess it is talking about that. So let's take a look. We've got some angles measured here. This is 63 degrees, so that arc must be 63 degrees. Here's a 90-degree angle, so that arc right there, DE, must be 90 degrees as well. Let's fill in something else that we might know. This is 63, so that means by vertical angles, that's 63. So this arc right here is 63 degrees. All right, that's pretty good. Let's see. We could find some other things, but I don't think we need to find this little one. We can just go from there. Let's take a look. We want to find out what arc AED is equal to. AED. So let's kind of mark it out right here just so we know which one we're talking about. You start at A, then you go through E, and you hit D. Even though this is not a semicircle, they can still use 3 letters to indicate it. They could have just said AD. They didn't need the E in there, but they threw it in there anyway. So we want to find that pink arc right there. Well, this is 63 degrees. This is 90 degrees. They're adjacent arcs, just like we talked about. And so what do? You just add them up. Pretty easy. So here's how we show our work. 90 plus 63, that would be 153. So the arc from A in this direction all the way to D is just 153 degrees. That's not too bad. Let's take a look at arc ADB. So A, and then D, and then B. Now that definitely is a major arc. So let me make that a little thicker so we can see it better. So I'm going to go all the way from A through D, all the way until we hit B. So that's the big arc I want to find right there. You could do this a couple different ways. I'm going to look at it like this. Watch. We went around this whole arc. You could do that, but watch. What is the arc from E to B? From E to B, this is a straight line right here going through the center. So from E to B is 180 degrees. Do you see that? So from here to here is 100. It's a little thick. because I drew that line with that point size, but from there to there is 180 degrees. Does that make sense? And so we want to find from A to D to B. So really, I want to find all of this. So that's pretty simple. Look, this is 63, and that's 180. So what do we do with that 63 and that 180? Well, we would just add them together, just like that. That's 3, that's 4, and that's a 2. So that's 243 degrees. So that big arc from A, that major arc, remember it's more than 180, from A to D to B is 243 degrees. All right, let's talk about one more thing as far as arcs, and we'll be finished. Now, we've been talking about the measure of the arc, talking about the angles, okay, or the degrees, sorry, measuring it in degrees. That would be the measure of the arc. That's how we measure an angle. But on this little key concept, or whatever they call it, we want to find out the length of the arc. How long is it? Not how many degrees, but if I took this and I snipped it right there and right there, okay, let's say it was a string around a circle, and I cut it here and I cut it here, and I wanted to measure, and I held it out straight, and I want to measure from here to here. That's what I'm looking for. I'm looking to see how long that line is, okay? So I cut it here, make a straight line, and I measure it, and I've got a length. I want to find the length, call it L, that's a lowercase l. I want to find the length of this arc. How in the world do we do that? Well, we know something about length. We did it in the last lesson. We know the distance, or the length, around the whole entire circle, and that would be the circumference. The whole entire circle would be 2 pi r. But we're not trying to go around the whole entire circle. We are just going around a part of the circle, okay? A fraction of the circle. So I'm just going from here to here. I didn't quite hit right there, but you get the idea. I want to go from here to here, and I want to find out how long will that distance be. So if I'm walking around a circle and I want to walk this from here to here, and I walked a 100-degree arc, I want to find out how far did I walk. So we can do that. We can figure it out. Now we would have to know the radius. Let's just make up a number. I just made up that 100 right there. Let's make this like a 5 or something. So if I wanted to find the whole entire circumference, what would I do? I would go 2 times pi times the radius, which in this case is 5. 2 times 5 is 10. 10 times pi, let's see, that's 3.14, so it would be 31.4. So that would be the distance around the whole entire circle. But this blue right here is not the whole entire circle. I'm not going to be walking 31.4. 31.4 would be going all the way around to here again. I just want to walk 100 degrees of the 360 degrees. Hear what I just said? I want to walk only 100 degrees out of, and we always do divide, we do out of something, 100 degrees out of the possible 360 degrees. That's the fraction, that's the decimal, that's the percentage, if you want to look at it, of the circle that I'm going to walk around. So that's what I do. I go 100 over 360. You don't even need the degree symbols there. Just kind of do that by force of habit. But all you need is 100 over 360, and then what? 2 pi r. In this case, the r is 5. So that's how we find the distance around here. See, that's the fraction that we would be walking, right? I don't have to do these individually. I don't have to figure out this is 31.4 and then do all that. I just put it all into a calculator and see what I get. So let's get our calculator out and put it in there and see what we come up with. I would do this first. There's several ways you could do this, but I would go 100 divided by 360 first and get an answer for that. So that's 0.27. What you're doing is you're walking around. 100 degrees would be about 27 or 28, or around at 28% of the whole entire circle. That's what that number is giving you. And then you take that number and you multiply it by, let's say, 2 times 5, which is 10. We can do that in our head. And then times pi, which would be this number right here. And you get an answer, and it's around 8.7. So the length would be about 8.7. Now, this is not in degrees. Remember, this is the length. It's how far you're actually walking. So if this radius was like 5 inches, of course, this wouldn't be much of a walk if it was 5 inches. Let's make it something else. Let's make it miles. Okay, let's make it 5 miles, big old circle. and the radius of the circle is 5 miles. So what would the length, the distance around this arc be? It would be 8.7 miles. So that's what you're going to do right there. So here it is. This is not a general formula. They give a general formula in the book, but I thought this would make more sense if I threw some numbers in there. So if you wanted to find the distance around, you don't do the whole circumference, right? That would be the whole circumference. You do a fraction of the circumference, or a part of the circumference. So you take the degrees, divide it by 360, then you multiply it by 2 pi r, the circumference. And you've got the distance around the circle. As long as you know the radius and you know this central angle, you can find out how long it would be to go around that circle. Let's do an example, and we'll quit. Okay, here's the last example that we're going to do. They give you this central angle, which is 80 degrees. Now look at the 14. They just kind of stick it there. It looks like it's just kind of floating around. It's not really between any 2 points. So what is the 14? The 14 is the whole entire diameter, right? And we're not using diameter. What are we using? We're trying to use radius. So if the diameter is 14, the radius is 7. I could put the 7 here, or I could put the 7 there. Both of these are the radii, from the center to A, the center to B. So now I should be able to figure this out. What portion of the circle are we walking around? We're only walking around 80 degrees of the whole circle. 80 degrees out of what? What's the whole circle? It's 360 degrees. And then you just put in a 2 pi r. Or, watch, remember we learned this in the last lesson? 2 pi r is the same thing as pi times the diameter. So, since they gave you the diameter, we could just use that, couldn't we? So we could just go pi times d, which is 14. If we would have split it up, you'd still have the 2 times 7, and you still get the 14. Chuck that in your calculator. I'll let you do that on your own, and you should get around 9.7 or 9.77. They ran those 2 places. Okay, 9.77. It's in meters, so it's meters. It's not degrees. You're not finding an angle. You're finding the actual distance that you traveled from A to B. And that's what you're finding. You're finding that length, and that length is about 9.77 meters. All right, hope that makes sense. I believe, yep, that's the last example, and that's about measuring angles and arcs.